wrote here, I'm going to have here as first part 1 over 2 square root of, well, here it's telling me put g of x. So I'm going to put g of x, which is x squared plus 1. So this takes care of the first part. Notice that I'm not writing 1 over 2 square root of u, because my function capital F is evaluated in g of x, it's not evaluated in u. Okay, when I use the chain rule. Am I done? Not yet, because I have to write g prime of x, and this is a little bit more familiar with, you have to take just the derivative of g, which is 2x. Then it just so happens that I can do a little bit of algebra and rewrite this in this way. But, this is just cosmetics. There is nothing besides a little bit of algebra. Okay, so now you can ask, why are you teaching us a game now in A, besides to give us a break from the hateful integrals? Well, the point is that the thing that I'm going to do next, besides trying to turn on the skip to do it. Does anybody actually look at that screen there as it is half baked? Are you happy with that? Yeah. Okay, great, thanks. So in integration theory, we don't deal with derivatives, but actually we do only we look at them backward. So if I can make a good use of the formula that I have here, the chain rule, let me just give it a name to emphasize that it's a version of the chain rule that you have learned, and I hope that even if the notation is a little bit off, it doesn't distract you too much. So, what is this formula telling me? So I'm going to erase, are you okay if I erase everything except the chain rule? So I erase all the red part. Okay. So what is the chain rule telling me? This is telling me that the function capital F of g of x is the antiderivative of the function f prime g of x, g prime of x. So I'm reading the chain rule, having in mind integrals. This is a statement about the derivative of capital F of g of x, and I can read it as saying that capital F of g of x is the antiderivative of f prime g of x, g prime of x. Why do I care? Well, let's assume that I'm asking you to find the antiderivative of this function. Then you're going to tell me, well, that is capital F of g of x. Just stated it. So this means that the integral of f prime g of x, g prime of x, dx is f of g of x plus, here I wrote d, I should have written an antiderivative, please indulge me, because as usual, antiderivatives can find plenty to study constants. So, if you can transform in one way or the other your integral in this form here, the one that you're trying to compute. And if you can rewrite in this form, then you can find the antiderivative in the way suggested. Now, you can do a little bit more, namely, let me move this screen up. And what is a little bit more? So, when you study the notion of derivative, you introduce perhaps the notion of differential. If you haven't, I'm going to give you a very quick review of that topic. And what is the differential? So we have an independent variable x, and the differential is dx. It's just a symbol that refers to a small increment of the independent variable. Now, besides independent variable, you have also dependent variables. Y, that is some function of x. I will pick, not by coincidence, the function to be a function g of x. And you have the differential dy, that just like the variable y is not free to go wherever it wants, it's related with what x does, it is a function of x. The differential dy is tied with the function g. So it's g prime of x dx. Okay. How do we remember this relation here? Well, just remember that in what is called the Leibniz notation of derivatives, dy over dx is g prime of x. So you can think of this as the result of flipping the x from the bottom to the top and vice versa. It's an easy way to remember. If you remember one formula, you know the other. Well, why I am saying all this? Well, because look at the expression that we have in the box here. This is telling me that if I isolate this part here, let me change color. If I isolate this part here, this is nothing else but dy. And this part here is f prime of 1. At that point, the statement on the right, the part on the right, f of g of x, is simply the function about it. What did I do here? I have rewritten my integral, substituting the variable x, the independent variable x, with a new variable that I momentarily refer to as y, but more often than not, that is referred to as u, hence the term u substitution that is popular among students. And not among instructors, but that's not anything that you should care. So let me look at some simple examples of this, in which it really looks like I'm doing nothing except rewriting the same soup in different ways. But it's this rewriting that will bring to stand out the function f prime, and therefore the function capital F, which is what we need to compute the integral. So, I should just rewrite this. So we have the integral of f prime g of x, g prime of x dx, and this is f of g of x. Here I'm remaining in the realm of indefinite integrals and derivatives. Essentially, we will discuss how to deal with the definite later on. So let's look at an example that is the following. I'm asking you to compute the following integral, 7 plus x to the power 4 to the power 8 multiplied by 4x cubed. Okay. Now, can you compute this integral now, or actually say half an hour ago? Could you compute that integral? Yes, because this is a polynomial. So if you have the time and the guts to compute that polynomial explicitly, it's a polynomial of degree 35, so it will take you quite some paper. Just multiply all the terms, it will take you a long time, but you can compute it piece by piece. It's doable. Is it convenient? Not really. Chances are you're going to make a mistake in these calculations, if the algebra is convoluted. But you can make the following observations. So, this mess has two parts that stand out. I wrote it in a slightly paved way, but that should work. One is this part here, which is a function that you're raising to the 8th power, and then you have 4x to the power 3. And what can you say about 4x to the power 3? Well, 4x to the power 3 is the derivative of 7 plus x to the power 4. Make sense? So, if you refer to this as g of x, the part in red, so 7 plus x to the power 4, this is going to be g prime of x. Well, then what is the function f prime that we're dealing with? Well, is the function, and now on purpose I'm not going to write anything, is the function take the power 8. Are you with me on that till this point? So I've broken down that weird term of the example to terms that contain g prime, and an imaginary f prime. I say imaginary, but it is just the way I'm interpreting the part of the expression under the integral. Well, if this is f prime, what is going to be f? I'm going to still write a blank here. This is a function that is function power. So I know the antiderivative of power is 1 divided by n plus 1 blob to the power 8 plus 1. So it's 1 over 9 something to the power 9. Are you with me on that? Now, I could have, and I will now, for those that prefer like that, I could write this way. This might make it more comprehensible for some of you, or the same for others. Whatever way pleases you, you can read it green or wrong. Okay? Yes?
You got the 9 taking the derivative, finding the derivative, and we get the derivative of that, right? X plus, you found the antiderivative of 7 plus 4x. Rather just
I'm not finding the antiderivative of 7 plus x to the power 4 yet. I found the antiderivative of the function power 8, or u to the power 8 if you prefer. Okay. And so now I've not yet done anything because I've just been redressing the left-hand side with two pieces of information that I'm going to use. The first is, as my goal is to write this is what the chain rule tells me, I need to write f as a function of g of x. And I know now what is f. F is 1/9 blob to the power 9. And to find exactly what it is, the blob is going to be g of x, and g of x is 7 plus x to the power 4. To the power 9. And that's it. This is the anticlimactic moment. There is nothing else. So the formula here that we obtain by integrating the chain rule tells me that I don't need to worry about all this part. I need to worry about finding the antiderivative of the function f prime, which is what I did, and then I'm done. Now you're going to ask, what happened to g prime of x? G prime of x has been taken care of by the chain. So here I need to find only the antiderivative of a part of my given. I'm precise mathematically when I say a part of my integral. This is a building block which talks to the other. I'm talking of f prime of g of x and g prime of x, so the two parts are related, but I need to focus my attention on one. Now, it might help in understanding why this works. So, here, at this point, the average person should say, okay, this may be true, but I don't believe it. In order to help you to believe it, I can offer the following. Let me erase what I have here. And think about the process that you do if you're trying to take the derivative of this stuff here. So I'm going to take the derivative, and if I do the calculation correctly, I'm going to end up with this piece here. That's what integration is about. Okay? So what happens if you take the derivative of this part here? Well, the first thing you're going to tell me is chain rule. I have an outer function, power 9, and an inner function, 7 plus x to the power 4. So what would be the derivative of the left and of the right hand side is going to be 1 over 9 multiplied by power rule 9, 7 plus x to the power 4 to the power 8. And then I have the derivative of the inner function, which is 4x cubed. Are you with me on that? So now the ducks, as you see, are lined up. I cancel the 9. They are lined up to get exactly the two terms that you see here. So it's not like we've forgotten this part here, 4x cubed. It just comes as a tail of the chain rule. Yes?
Is that the antiderivative of what after you
If I answer going to your question, yes. The stuff that you have here is an antiderivative of this.
What about the thing below it?
Sorry?
What about the red thing below it?
Sorry, what about that?
What about the red thing below it?
This?
Yeah.
Oh, this is exactly the same. So if you see, this is 7 plus x to the power 4 to the power 8, 4x cubed. So I proved this twice. So this should be enough in the sense, if I apply the chain rule correctly, I should find this to be an antiderivative. Okay? Now, if I don't believe it, I can verify that by getting my answer and taking the derivative. I ask you, what is the antiderivative of cosine? You tell me sine. If I don't believe you, I take sine, I compute the derivative, and I see what I get. There is nothing more convoluted than that. So now, what is the name of the game and what we're going to do now on is find the g of x. So what allowed me to solve this problem here was I was able to identify g of x explicitly. And I picked the 7 plus x to the power 4 because I've been doing this job for 30 plus years. For you, it's going to be a little bit more challenging. I think it's going to take you less than 30 years to figure out what is the right choice for g. G prime of x here was very evident. It was just nearby. So your choice of g of x is confirmed by the g prime of x that should be able to read quite fast. Maybe this example is not the easiest, but easy enough. What happens if you don't see clearly what is g of x and g prime of x? Well, we're going to see how to do with that, and how to force g prime of x to appear in the picture. I think there was a, yes? Sorry, let me get closer. Trying to sugarcoat the multiplication by part. So you're saying I can write that as a prime of u prime dx? Yes, yes, yes. Yes. That's right. Yes. Yes. That is exactly what I wrote implicitly before when I was saying, well, g of x is y, but I can also represent x. Okay, so let's say you need to find this is what implicitly your colleague was saying. You need to find a new variable that is not an independent variable, is not x, but is a function of x, g of x, or if you prefer, we call it u, to transform your integral in something that is not an integral of x anymore, but is an integral of u. Yes?
How did you get from 1/9 times 7 plus 4x to the 9th power plus 8? How did you get from there to 7 plus 4x plus 8? And then it's
So, how I went from here to here? So, I applied the chain rule to this function. This is 1/9 multiplied by this to the power 9. So, the derivative is constant is 1/9, doesn't get touched. Then I apply the chain rule with outer function power 9 and inner function 7 plus x to the power 4. Okay? So, derivative of the outer function is 9 7 plus x to the power 4 to the power 9 minus 1. And then I have the derivative of the inner function, which is 4x to the power 2, which is the derivative of this inner function.
So you're just proving that that is in fact the integral of that.
Sorry?
You're just proving that 7 plus 4 is 7 plus x to the 4 times 4x to the third. You're just proving that that is in fact the integral.
Yes, yes. I verified that what the integration by substitution formula gave me, that is what is in the first line, is consistent with the fact that I can compute the derivative at the end of the day and check my calculation. Whenever you're computing anti-derivatives, this is an advantage. You can always check if your calculation is correct by taking the derivative. Go backward, and you should get exactly what you started with. Okay? And this is what I did here. And I didn't have to, in the sense that, you know, I completed the integration by substitution formula, but just to make it more clear. Okay, so the next goal is to hunt for this function, g of x, and raise it to the dignity of new variable, integration variable if you like, and get the integral with it. So let's discuss the example that I did in the beginning. It was for a definite integral, but I can deal with this independently. So I have this integral here. I take it as an indefinite integral. This example is simpler than the previous one that I dealt with, but it is in a sense too simple to really discuss generality, but still we want to learn how to do this. So I would like to see this as g prime of x, as g of x. The problem is that I don't quite have g prime of x in the neighborhood here, because g prime of x, so if g of x is 1/2 x, g prime of x would be 1/2, and I don't see any 1/2 lingering in here. But nothing forbids me from just forcing its appearance, so I call u to be 1/2 of x, that's my new variable. Accordingly, du is going to be 1/2 dx. And now I can make the 1/2 appear and disappear by just rewriting this as cosine of u. This is cosine of 1/2 of x. And the dx can be written in terms of du like that. Now that this is 1/2 dx by this result here, so overall this is exactly the combination cosine of g of x, g prime of x. This is g prime of x and this is g of x. And there is this 2 here that appears in the interim to compensate the fact that I didn't have 1/2 to start. So I continue here. And now I can take 2 in front, it's just a constant. And now I have a plain vanilla question. I'm integrating cosine of u with respect to u. So I need an antiderivative for cosine of u, and that is sine of u. And I can write it. This is just like writing sine of g of x. Am I done? Well, not quite, because actually I need as an answer cosine of g of x, or better to say, 2 times sine of g of x. Because the problem asks for a function of x, and I cannot give as answer something that depends on u. So to finish this problem, I have 2 times sine of 1/2 of x plus a constant. And this is the answer. Yes?
Sorry, where did you get the cosine u times 2dx, 2dx, sorry, d where did you get the cosine u times 2u?
Yes, so here I'm trying to show how, even if I don't have g prime of x readily visible, I can make it appear by doing algebra. So I've decided that I'm going to try to have g of x to be this fellow here, okay, which is the argument of cosine. And side remark, 9 times out of 10, if you have cosine of something in your integral, the something is the right choice for g of x. Okay. Then this is not quite of the form cosine of g of x times g prime of x dx. It is not, because the g prime of x is 1/2, and I don't see any 1/2 inserted in here. So this is not quite my integral. However, I can force its presence. I observe, well, the derivative is 1/2. I use, instead of g of x, for notational simplicity, I call this function here to be the new variable, the u. So I'm switching variable, I'm substituting x with u, and u is 1/2 of x, u is g of x. Well, if this is u, what is du? Well, the differential of a dependent variable, by the formula we wrote before, is the derivative, so this is g prime of x, multiplied by the differential of the independent. Okay, and now the next step is to rewrite this here. Let me erase this for notation of clarity, I hope. This is cosine of u, this part here. And that's the way I wrote it. What is dx in terms of u? Well, dx is 2 times du. I read it from this relation here. And that's what I inserted here. The x is 2 times the u. At the next stage, I take the 2 and I put it in front. This is just for convenience. And I'm left with an integral which is simpler than the one I started with, because now I have cosine of u. I don't have cosine of a function. So, how do I do substitution? So, I do substitution essentially in 2 stages. I identify in the blob that I'm trying to integrate something that could be the new variable. Usually, this is what you, in the back of your mind, should think as g of x. It's something that is containing cosine, in sine, in a power, in tangent of, in the denominator, something, in a square root. You want to get rid of it. You want to simplify it. This is your chance. You take that object and you call it u. Then you have to change the differential. So you need to know the relation between du and dx. But if you identify u, x, you know what du is. It's g prime of x dx. And you're going to flip it, use a relation, to write everything in terms of u. And once you've done that, if you're lucky, if you made a good choice at the beginning, you're going to find yourself with a function of u that you can integrate. If you didn't succeed, well, try again. So let me give you an example. So this example will be sufficiently complicated, so it's going to be let's make it long, why not? It's going to be x cubed divided by the square root of 1 minus x squared dx. It's quite unlikely that you can find that in an integration table. It doesn't come up right away. This would be anything simple. It's going to take a while to integrate this. But let's keep in mind the principles that we have. So we want to get rid of something in this integral that is making impossible to guess the antiderivative by using differentiation. Is x cubed a problem? Well, not really. Is the argument of the square root that is a problem, but 1 minus x squared that is really not. Do we get that? Then I need to pay attention to the fact that this is dx. If I transform this in u, or g of x if you prefer, I need to transform also the x, because I have to deal with oranges alone or apples alone. I cannot mix them up. So I'm going to take my function g of x to be 1 minus x squared, and du is going to be g prime of x dx, so it's negative 2x dx. Are you with me on that? Now, I have to be a little bit careful here, because this problem is quite more complicated than both the 2 examples that I've seen before. It will be a high number in your homework questions series of today's lecture. I have to transform this in square root of u, and this would be the easy part. But I have also other stuff that depends on x. And I have dx. So what I will do, that's customary, is that I will work with a hybrid expression that will contain x and u. Those will be intermediate steps. At the end, as I said, I need to work only with apples or only with oranges. So I have to switch from x only to u only. Okay? You cannot have x and u and treat one as a constant because it seems fair. It's not correct. So, for the time being, I'm going to transform this as, well, this I'm going to write as 1 over square root of u. Are you with me for this part here? Then I'm going to keep x cubed for the time being. Okay, this is hybrid notation. It's yucky, but it is useful. And then I need to write dx in terms of du. So really, I literally solve for dx. There are more elegant ways of doing that, but I will focus on what matters. So if I solve for dx, this is negative 1 over 2x du. Are you with me on that? So now I'm traded half of the apples for oranges. But I still have x and u around. Ugly means that the job is not done. Okay, very often students do one change and then they act as, oh, I'm not noticing that there are x's around. They act as if they are. Be careful. I need to do some algebra. This is the next stage. To get rid of x. Obviously, I don't want to get rid of u, otherwise I will go back to the first expression that I couldn't integrate, so it would be a waste of time. So first, I can cancel here this with this. Are you with me on that? Enough. And then I need to write that in terms, let me write it again, just for a convenience. So we have a minus sign in front. So the minus sign that comes from here, I have 1/2 that comes from the 1/2 here, x squared divided by square root of u, du. And I'm not yet done because again I have still apples and oranges. I need to write x, rather say square in terms of u. Where do I find x squared in terms of u? Well, I go back to this formula here. This allows me to write x squared in terms of u because I can solve for x squared and say, well, x squared is 1 minus u. Are you with me on that? And now this is negative 1/2 integral of 1 minus u over square root of u. We're not done, we're just halfway there. Maybe let's be less optimistic, like 40%. So, what has changed? So, I left the x variable and an integral that I couldn't deal with, and I transformed it in a integral contains only u, that is less scary, because I have a quotient in which the numerator is 1 minus u, the denominator is square root of u. Better than square root of 1 minus x squared. Now, this problem is something that you can solve, but it's not among the easiest problems that you can solve. When I say you can solve, I mean just by looking at integration table, but it requires a little bit of attention because there is a few pitfalls, okay? So keep your eyes open here. First, it is written as a quotient, but as we have discussed, that is rarely useful. Okay? You don't want to find the antiderivative of the numerator and the antiderivative of the denominator. It's not going to lead you anywhere. Are you with me on this comment? Okay. So I need to use algebra to transform that in something that is more manageable. And I will do that by dividing each term by the denominator. Okay. So I'm going to do the following. I'm going to write this as negative 1/2 the integral of 1 over square root of u minus square root of u du. So I'm dividing 1 by square root of u and u by square root of u. Yes? Sorry?
Where did you get the 1 minus u from?
The 1 minus u come from the fact that in the substitution, I read that x squared is 1 minus u. Because u is 1 minus x squared, and I can solve for x squared. That's what I need. I need x squared. Okay, now I'm going to rewrite this, and I'm going to speed up a little bit because now we are in safer territory, hopefully. I can rewrite the first as u to the negative 1/2, and the second term as u to the power 1/2. Everybody with me on that? Using properties of powers and the definition of square root, if you like. And now I can apply the power formula. Integral of u to the power n. So this is negative 1/2 that multiplies and in the antiderivative. U to the power 1 divided by 1 minus 1/2, u to the power 1 minus 1/2, minus 1 divided by 1 plus 1/2, u to the power 1 plus 1/2, plus a constant. Here I've used twice the power formula applied to the function u instead of the function x, but nothing changes. Now I'm going to do some algebra to rewrite this, and this is negative 1/2. This gives me 1/2, so it becomes 2 to the power square root of u. And this becomes minus 2 over 3 u to the power 3/2, or u square root of u. Plus. Am I done? No. I'm not done because the problem asks find the antiderivative of a certain function of x, and I'm answering in terms of u. I ask you the price in dollars, don't give me the price in euros. You need to convert back. So I can do the algebra if you like or not. This is minus square root of u, which is minus 1 minus x squared, because u is 1 minus x squared. And then I have plus 1 over 3, 1 minus x squared, square root of 1 minus x squared. Yes? Sorry?
Where did you get u times the square root of u from?
From u to the power 3/2. Okay, a couple of comments. The first is, and I invite you to verify, you could have solved this problem choosing as new variable this. So instead of choosing 1 minus a square, you choose as new variable square root of 1 minus x squared. It is the same level of the figure. It's less obvious, doesn't come up easily to mind, but it would lead to the same type of task. None is better than the other. Okay, you have to go from here to there, you can exit from here, exit from there. Sometimes it's good. Second, some of you might have noticed that if instead of 3 here I add 2, I would end up after simplification with a 1 here, which means that here I would have a 1. And then I need to write x as a function of u. So what I'm trying to tell you here, I can give you a minor modification of this problem in which you have x to the power 2 instead of x to the power 3. proceed exactly the same way I did. You arrive here, and you're stuck. You can't proceed. Substitution doesn't work for that integral. If you think long enough, it'll be a long time. X1, all the power, substitution will work. X1 even power, substitution doesn't work. There are methods to deal with that. Maybe not we're gonna discuss, but it's a hit or miss. If you add power 2, it's not like it would pop out that substitution doesn't work. It's trial and error sometimes. It's like choose U or V, the other choice that I made. If one works, the other doesn't. Or both work. It's difficult to say beforehand. Question? Yes?
I'm sorry, I'm still looking through that defense with
Sorry?
Iverman.
Okay. Yes?
You need to scroll down again. I just want to make sure I got the right.
You want to scroll down?
Yeah.
Sure. Is this good?
Yeah.
Okay, now I'm going to use, I'm going to look at another couple of examples. I'll start with this. And this is an integral that occurs often in statistics. It's related with the Gaussian distribution that we have mentioned perhaps at some point, at least implicitly, that I will mention again. This is the first momentum distribution, whatever that means. If you take that, we will see this tableau. And here we proceed by substitution in a way that is very similar to what we have done at this point. We have the exponential of something. We don't like the something in the sense that it's an x squared, so we choose u to be, say, negative x squared. What is du? Du is therefore negative 2x dx, which means that I can already notice that x dx appears in this, so I can solve for x dx, it's more convenient. X dx is negative 1/2. Everybody with me until this point? So I've identified a candidate for you, and now I'm trading everything that depends on you with the terms that depend on, everything that depends on x, terms that depend on you. So this becomes x dx is going to give me negative 1/2 du. And e to the negative x squared becomes e to the power u. I'm going to write this by shifting the constant out of my sign this way. Now I have to find the antiderivative of e to the power u, and the antiderivative of e to the power u is e to the power u, or at least the choice of antiderivative. And this gives negative 1/2 e to the power u plus a constant. And I'm not yet done because I need to write everything in terms of x. sorry, did I cancel too early? Are we good? Okay. Good. Our example is the following. I'm gonna consider this function here. This doesn't seem to be that complicated, but it is, in the sense that, as far as I can see, it's not easy to solve it without substitution. And there are two ways that you can proceed here. As I said before, those two ways will lead to comparable level of difficulties. You can really pick and choose. You can choose u to be x plus 1, or u to be square root of x plus 1. I'm going to follow the second route, square root of x plus 1. Because again, I need to write everything in terms of u, and well, du is going to be 1 over 2 square root of x plus 1 dx, which means that dx can be written in terms of du as 2 times square root of x plus 1 du. Everybody with me on that? Okay, so now having a hybrid expression, this becomes, well, dx is 2 times square root of x plus 1 du. So I'm going to have a 1/2 here in front to compensate x and du, where I've absorbed this entire term here and here. Now I have to resist the urge of integrating x with respect to u. Okay, get the derivative is not x squared here, because I'm integrating x not with respect to x, but with respect to u. Apples and oranges. I need to write x as a function of u. And how do I read that function? Well, it's not completely obvious, but I read it from here. This is similar to what happened before, but it's a little bit more convoluted here. I square this formula to get x u squared is equal to x plus 1. Which means that x is equal to u squared minus 1. Yes?
Should that be a 2 from the integral on the last step on the right side from the top? You got 2 on the bottom left. So it looks like it became 1/2.
Oh yes, it's 2. Yes, thank you for pointing that out. My mistake. So we erase this, and what your colleague observed is that dx is no, sorry. Okay, so moment of embarrassment. So I have. Oh yeah, I really messed up. Sorry. I wrote it up correctly. Please indulge me, and let me cancel this part here. I read it backward. Okay, so let me go back here to the substitution that was the source of the mistake. dx is 2 times square root of x plus 1 du. So I can rewrite this as integral of x square root of x plus 1, and now I plug in the dx, that is 2 times square root of x plus 1. du. Okay? Now, so this block here, dx is 2 times square root of x plus 1, which is what I wrote here. So this corresponds to the term. Now I'm going to rewrite the rest in terms of u. First, I'm going to notice that this is x, this is u. I'm trading term with term. This is 2 times u, and this is du. So this is, putting everything together, 2 times integral of x u squared du. Now I'm at the point in which I stopped before. I need to write x as a function of u. And in order to do that, I take my equality here, and I say that, well, u squared is x plus 1, which means that x is u squared minus 1. And this yields 2 times integral of u squared minus 1 u squared. I'm going to do the algebra, write this as u to the power 4 minus u squared du. Okay, fair enough. The antiderivative is now 2 over 5 u to the power 5 minus 2 over 3 u to the power 3 plus a constant. And to complete the exercise, I have to rewrite my answer in terms of x. So u is square root of x plus 1. And so this becomes 2 over 5 square root of x plus 1 to the power 5 minus 2 over 3 square root of x plus 1 to the power 3. Plus a constant. And this is the answer. Now, in the last 10 minutes, we're going to discuss what happens if you have, instead of an indefinite integral, a definite integral. So, instead of being asked to find antiderivatives, you're asked to determine, say, a signed area. And I'm going to start with this example here. I'm going to work the number of example, integral from 1 to u of dx 3 minus 5x to the power 2. Here, what this integral is asking me is to compute a number, not to exceed the function. And I can proceed in 2 ways. The first is forget about the definite integral. Focus on the function 1 over 3 minus 5x squared and find the antiderivative using integration by substitution. The choice will be, as we will see, of u to be 3 minus 5x. And then, once you've completed an antiderivative in terms of x, plug in the n values. Okay? This means doing 2 steps. Transform my function from x to u, and then transform it back from u to x. In the case of a definite integral, I can skip 1 step by transitioning from x to u, not only with the function, but also with the endpoints. So, the meaning of these endpoints is that x ranges from 1 to 2. So in the beginning x is equal to 1, and then x is equal to 2. Now if you introduce a new variable, a variable being will change accordingly. So I'm announcing that the following method will work. I will choose u to be 3 minus 5x as new variable. Is this a good step? Yes, because instead of having 1 divided by blob to the power 2, I will have 1 divided by u to the power 2, which is easier to deal with. And well, what happens to u? Well, when x is equal to 1, u has the value 3 minus 5, so it's negative 2. When x is equal to 2, u has the value 3 minus length, namely negative 7. So I will solve this definite integral by changing not only my function from the variable x to the variable u, but also the endpoints, matching the value x equal to 1 with u equal to negative 2, and the value x equal to 2 with u equal to negative 7. Specifically, I'm going to do the following. So this is my new variable. Du accordingly is negative 5 dx. And so this becomes the integral from negative 2 to negative 7. Du is, dx is negative 1 over 5 du, and this is u squared. And I rewrite it for cosmetic convenience like that. Negative 1 over 5, integral from negative 2 to negative 7, du over du. Okay, 2 comments. The first is, now I have a definite integral for the variable u with endpoints negative 2, negative 7. I will compute it. I don't need to go back to the experiment. Second comment, some of you might have noticed that the endpoints for the x variable were 1 and 2. So the left hand point was smaller than the right hand point. As I changed variable, the endpoints have flipped. Now the left hand point, negative 2, is actually bigger than negative 7, right? Should I flip them? No. I still need to match left hand point with left hand point, right hand point, and left hand point. Even if they flip the order, this is taken into account by the sign. So if I could change the differential of u gives you the differential of x, and then actually have a minus here, which in a sense is the reason why the endpoints are flipped. But you don't have to worry, just match this guy with that guy with that guy. Not the largest with the largest and the smaller with the small. Okay? Left with left and right with the right. You don't care which one is the biggest. Okay, now we can finish. And I will actually erase everything here because I don't need to know at this point how I got this integral here. I just need to compute it, and I'm going to do it by using the power formula. There we go. This is negative 1 over 5 integral from negative 2 to negative 7 of u to the negative 2 du. And the antiderivative is 1 divided by 1 minus 2, u divided by 1 minus 2, evaluated in negative 2 and negative 7, and this gives negative 1 over 5, and this gives you minus 1, therefore I'm going to just flip the sign, 1 over u, negative 2 and negative 7, this gives 1 over 5, negative 1 over 7 plus 1 over 2, algebra, this gives 1/5. And this is 14 -2 plus 7. This gives miraculously 1/14. Sorry, I'm afraid it's very readable, but its last calculations are hopefully not too challenging before. So, again, definite integral, we do the same shebang for the function that we did in an indefinite one, but if we change also the endpoints, trading the x value with the u value, we have the advantage that we don't have to go back and retransform my integral. And so this makes this a one-hop operation instead of one. Okay, so I will try to do a few more examples in Thursday's lecture, and then on Thursday we're going to start integration by parts. Next Thursday, not this one, but the following one, there is the midterm. The midterm will cover half integration by parts. Okay? So integration by parts will be discussed on Thursday